Tell me when it's coming through. Okay, awesome. Welcome to the UNSW Mathematics Society's Math 3411 workshop. So this will be the workshop covering content for the code information, codes, and ciphers. Nice. I will be presenting today so my name is Jimmy, and along with Matthew and Cyril, we'll be covering the content for this course. So to not waste time, just one sec. I think I gotta reset the stream here. Give me one sec. Okay, awesome. Sweet. Let's get into things. So just a bit of an overview over the content that we'll be covering between today and tomorrow. First, we'll go over a bit of an introduction to codes and ciphers, and the basic codes such as the ASCII and ISBN code, then error detection correction, compression coding, and then tomorrow on Tuesday, we'll be going over information theory, number theory and algebra, algebraic coding, cryptography. Awesome. So first of all, an introduction to codes and ciphers. So what is this course all about? It's all about encoding and decoding messages from a sender and a receiver, as well as considering the potential noise or errors that could occur during transmission that could cause the information to be corrupted. And it's all about how can we detect these kind of errors or noise, and also how can we correct them. So our first definition here is going to be a source alphabet. It's going to be defined as a set S, which all the elements will be the letters of the alphabet, right? And each of these elements also have an associated probability. A good analogy for this is our English alphabet. So you can think of the letters in the set being the English letters, A through Z, and these form words. And each of these letters have a probability of occurring in common messages, right? So you'd expect the letter E to have a higher probability compared to a letter Z. A code alphabet, however, is going to be defined similarly, and we can encode messages using a code alphabet. So, for example, here we have a source alphabet A, B, C, and a code alphabet of 0 and 1, right? And the code alphabet will form our code words, which we then can create a mapping to our letters, right? So we say A maps to 0, B maps to 1, 0, C maps to 1, 1. And then using this, we can now encode and decode messages, right? So we replace, if we have an original message A, B, B, C, we can replace each letter with its encoding, right? And then that will form our new code word. So A goes to 0 here, and then B goes to 1, 0, 1, 0, and C for 1, 1. Going over some of the prerequisites. So we have modular arithmetic, right? If you guys have done 1081, you'd be very familiar with this. So most of the operations we're going to be doing in this course will be modular arithmetic, typically defined by mod M. Any operations that we do in this, such as addition, subtraction, multiplication, will result in the remainder after dividing any number by the number m, right? And the remainders are going to form the set of the integers from 0 to m minus 1, right? So for example, if we're doing binary, we're going to be doing like 1 plus 1. And if we're working in Z2, right, this is going to equal 0, as 2 is equal to 0 mod 2. The division algorithm as well says that for any integers a and b of z plus, there exists unique integers q and r with a equals to bq plus r, right? Additionally, if a is congruent to b mod m and c is congruent to d mod m, then addition, subtraction, multiplication across all the congruences still hold. So we can perform all our maths. Briefly, also some probability is needed as well. So the binomial distribution describes the probability distribution of a random variable x that can result in either event E or e to the c. And this is going to represent the probability of an event occurring and the event not occurring, right? Where the respective probabilities p and 1 minus p. And it has the following probability mass function. So this is going to be a descriptor of the probabilities. And we also have Bayes' rule too, which is going to give us the conditions of an event X occurring given that a different event Y occurred. And this will be covered later as well. So finally, we move to our first code. If you guys have done computer science, you should be very familiar with the simple ASCII code. And it's just going to be a way we can represent letters or symbols in binary. So it's defined as a code where each symbol is encoded as a string of exactly 7 bits, with each bit being 0 or 1. I think there's an example here. Yep. So A may be encoded as 0110010. The extended ASCII code, however, is going to be an example of a code that has a feature of error detection. So what we do is we take a regular ASCII code word. So for example, for A, we have 0110010, and we add a check bit at the very left. And this is going to ensure that the amount of ones or zeros in our code word has even parity, right? So for example, for A, since we have 3 ones in the code word, we would add an additional 1 such that we have 4, an even amount of ones. So this is going to be the letter A in the extended ASCII code. The 8-bit ASCII burst code building off the extended ASCII code is similar, but instead of just extending a single word and then having a parity bit, we will now take a group of words and construct an additional word to ensure that the columns, if we put the messages into a matrix, have even parity, right? So this last row at the bottom isn't necessarily going to be a code word, but it's going to be something we call an end of transmission block. And it requires, similarly to the check bit, that each column has even parity, right? So if we have these 3 code words that represent these 3 source words, if we look at the parity here, we've got 2 ones, so we put a 0. If we have 3 ones, then we put an additional 1, right? And then if we have 2 ones, then we have a 0, and so forth. A feature of the ASCII burst code is now that we can detect errors. So for example, if we had like a cosmic bit flipped and this becomes a 1, we can now inspect the parity of each row and each column to detect where the error is. You should be very familiar with this if you did test 1. I think this was a question. So going through each row, we can see, okay, nice. This is even parity that passes our check, which is also called the syndrome, which I'll get to later. This row now has 3 ones, which has odd parity. So we know an error has occurred, but we do not know the position of the error, right? This is fine. This is fine. And then going through the columns, it looks like this. And now we can locate, okay, this row has an error. This column has an error. And now we have an intersection, which represents where our error occurred, right? So we know, okay, that was flipped, and we can correct our error and retrieve the original message. Going on to the next simple code, we have the ISBN code. If you look on the back of the books, you'll see this all the time. This is the ISBN 10 code, which I think is outdated. Now they normally use ISBN 13. But nevertheless, they have a different condition, right? So this condition is the syndrome. And it will define how we know if an ISBN code is valid or not. So normally, the information bits will be the first 9 bits, and we have a last bit being a check bit that is constructed to satisfy this syndrome. The syndrome is that each of the 10 numbers multiplied by its position, so this I is going to be its position, right? and then this is going to be the value at each of those positions. Each of the multiples summed together should be congruent to 0 mod 11. So for example, this number is a valid ISBN, and the way we can check this is by checking this against the syndrome. So we will take the first number, right, and multiply it by the value there. The second number, multiplied by a value, and so forth. This will probably give us a very big number, and then it should be congruent to 0 mod 11, which is very nice. Similarly, for the other number, as it's not a valid ISBN, we know that it is not congruent to 0. Some features of the ISBN 10 error detecting code is that it can detect errors including a wrong digit or the interchanging of 2 digits, and I believe Brits has a really nice proof for this in the lectures. Okay, so codes like this are important because they can appear in the final, and as we just discussed, the question could be like checking if there's a valid ISBN. So just before, we would sum all of the numbers and check what this is. So writing this out again, it would be 1 times 0 plus 2 times 9 plus 3 times 0, so forth. And if we look down here, this is equal to 208, right? And using modular arithmetic, I believe in the final exam, we have computer programs to assist us, right? So I would recommend a program such as Python or MATLAB or even Maple to verify that this is equal to 0 mod 11 or not. Note that here we don't use the congruence, but instead we say it's not equal to 0 as we specify we are working in mod 11. As it's not 0, it's not a valid ISBN. But consequently as well, a question that we can ask is that how can we make this valid? As I said before, this is a question that has to be considered when creating an ISBN code for a book example, as we have 9 information bits and we need to add a check bit to make it a valid ISBN. This is not an error detecting code, however. This is not error correcting code, but detecting code. So given an invalid ISBN, we wouldn't know where to what number to change to make it valid. So in this example, we can take the check bit and transform it. So we know that the first 10 numbers summed together is going to be equal, or the syndrome of the code is going to be equal to 208, right? And we're saying 208, if we take away the last number multiplied by its position, so that's going to be 4 times 10, right, minus 40, this should be equal to the sum of the first 9 numbers, right? And then with the proper last number, this should be 10, this should be congruent to 0 mod 11. Simplifying a bit, we can do 168 plus 10x 10 is congruent to 0 mod 11, right? And then we can take this number to the other side and then perform the extended Euclidean algorithm for those who have done 101. But as you might know, it is very lengthy, and for a problem of this caliber, kind of overkill. What I would recommend, and I think Brits recommends as well, is simply guess and check. As we're working in mod 11 here, x10 here can only take 11 different values. And I mean, even using a calculator, just sub in from 0 all the way to 10 and see which of these values make the equation hold, such that the summation is congruent to 0. And seeing here, the only solution for such is x10 is equal to 3. So that's pretty nice. We get it early on if you were guessing and checking. Thus, it's a valid ISBN. Okay, now we are up to topic 2, error detection and correction. So this will all be about your Hamming codes and parity check matrices. So as we said before, any questions as well? Yeah, okay, great. Sweet. Okay, so as we said before, we're now going to be more focusing on how can we detect and correct these errors. So on the idea of noise, so what is noise, right? We can think of it a kind of disruption between a sender and a receiver. And we look at, in this chapter, the ability of certain codes to detect and correct these errors. There's an example of a transmission here. So if we have a bit, we have a probability P, which is the probability that there's going to be an error. And you can see here, we might receive an 1 incorrectly. Or conversely, if there was no error, there's a probability of 1 minus P that we got the correct information, right? And same for the other code letter. And the two codes we covered before were examples of pretty generic codes that have the ability to detect or correct errors. So the first code in this chapter we're looking at is the binary repetition code. So it's a code that simply repeats a particular symbol a fixed number of times. So if we were sending the message 0, we could take the binary repetition code of length 5 here on this odd side. And we can see if there's one error, right? Our message still is preserved as it's the majority. So if there's only one error, we can take the majority element and still retrieve our original message. So we still get 0 here. In this case, 0 is also the majority. But you can see here as well where the repetition code fails us, or the extent of what it can correct errors, as the error takes the majority and we incorrectly decode to 1. In the even case, where we use even amount of repetitions, you can see here we achieve 0, 0. But in this case, there's an even amount of ones and zeros, right? So this is going to be an example of where a code can correct errors, but also only detect in some circumstances. So we know there is an error here, but we don't know if the sender originally sent a 0 or 1. So we just mark this as an error, right? Detected. This is a 1. This is a 1. Pretty nice. I think we'll cover over the intricacies of how much we can detect and correct later. Yep, so there's 3 strategies as well here. So you see that if we said that we'd always take the majority element, there's some circumstances where we would overcorrect and take the wrong message. So the first strategy that we can employ is only correct up to 1 error, right? So we say, okay, this decodes to 0, and as well, this decodes to 1, right? Because we interpret 0 as the error. But if there are 2 errors, then we will also just detect here. And then we also can correct up to 2 errors as well, as we discussed before. So that is going to be taking the majority element. There's also no correction, right? So let's just say we can detect everything. So it's just examples of how we can use a code to interpret messages. There's also a question you can ask yourself, why can't we correct up to more than 2 errors in this example? So if we were to correct up to 3 errors in this, you can see that, of course, then you also would be able to correct up to 2 errors if you were able to correct up to 3 errors, and you could decode this message as 0 or 1, right? And that's not really useful to us. The whole point of a code is that we can detect or correct errors, and in this case, we aren't able to come to a decision here. Yep. So for a 2t plus 1 or 2t plus 2, so this really is just a way of saying odd or even, and the reason we have this plus 2 here will come in later. We say that we can correct up to t errors, right? So for a length of code 5 here, or code 6 here, this would have been 2t plus 1. So t is equal to 2, which makes sense. We could only correct 2 errors here, not 3. Okay, moving on, we'll go into binary Hamming codes. So this is a nice protocol. It's going to be a code defined by two numbers, n and k, where the code words are of length n with k information bits, such that it is single error correcting, emphasis on single, and has a parity check matrix H of size n minus k by n. I'll also add on here, note that we have a length n code word with k information bits, right? So that implies we have n minus k check bits. And I'll just write down k information bits as well. And the code set is going to be generated from all of the code words that satisfy this equation, which is going to be our syndrome, which determines if a code word is valid or not. And that is the multiplication of the parity check matrix by the code word is equal to the zero vector. Right? For those who have done linear algebra, this implies that all of the code words exist in the null space of the matrix. So going on to example here, we have the Hamming 7-4 code, right? And this is the check parity matrix H. A question we could look for as well is why do we have 7-4 or not 6-4 or any other value of n? And the reasoning behind this is that we wouldn't have 3 check bits in that scenario as well, as we'd only have 2 check bits, and it wouldn't be possible then to 6 minus 4 equals 2, be able to then correct any codes or have a parity check matrix in that circumstance. Some properties of the Hamming codes is that the dependent columns, or I'll start with the independent columns of H are going to be the positions of check bits. It should make sense that we should be able to send any information of length k through this, and therefore the check bits must be fixed, right? So we assign the check bits to the independent columns, and we let the dependent columns be the mutable information bits. So in this scenario here, we can see that the first column, the second column, and the fourth column are going to be the check bits, and the other columns will represent our information bits, or the positions of our information bits. And the intuition behind here, we want a unique solution for the check bits as well, and that will only be possible when we have independent columns for the information. Only the related columns are independent to the information bits. So how will we use Hamming codes to correct errors? What we do is that we'll calculate our syndrome, and what's really nice about the property of Hamming codes is that the syndrome, if it's not 0, will be equal to the column vector in the position of the error. So example, if we have a corrupted message here, if it was not corrupted, then it should be equal to 0, 0, 0, right? But if it was 1, 0, 0, for example, we know then, since this vector is equal to the first column vector of the check parity matrix, this implies that the first bit in our message was an error. Note there's only one result we get here, and by this protocol, that kind of implies we are only able to correct one single error. So, suppose we're using the Hamming 7-4 code, we receive the message 101101, and we want to correct the encoded message and determine what the information was. So let me just copy this over. I'm going to take a screenshot. Okay. Oh no, that's rotating. Okay, great. So we'll take our code word or vector here. Note that code words are vectors. They are both the same way of saying the same thing. The different ways of saying the same thing, sorry. and we need to multiply this out. A nice trick that is taught is actually writing the vector above it. For those who have not done linear algebra, the way we multiply a matrix by matrix is we go row by row in the first matrix and column by column in the second matrix, right? And we multiply elements pairwise and sum them. So for the first number here, we'll multiply 1 by 1 and then add that to the multiple of 0 plus 0. So that's still 0 times 0, so that's still 1. 1 times 1 again, so now our answer is 0. 1 times 0, still 0. 1 times 1, that's going to be 1. 0 times 0, that's still 0. And then 1 plus 1 times 1 in binary will be 0, right? So we'll get 0 here. Going pairwise for our second row as well will give us 0 and 1. As we know that this vector is going to be the same as our column vector here, we can note that we have an error in the fourth bit of our original message. So going to our message here, we can correct it now, as there was only one other choice as we work in binary. The question also wants us to determine where the information was. And if you remember, the information are going to be in the dependent columns. So looking at leading terms, we can see what the independent columns are, right? So it was these ones. So these 4 bits here are going to give us our message. So looking at these 4 values, our message was 1101, which was nice to retrieve. Note that the error was actually in a check bit as well. So by fixing the error actually didn't change the transmission of the information bits, which was nice. And yep, going through here, yep, the information is 1101. Another example question from a final exam, 2018 Final 1E. Check whether a random string of 15 ones and zeros has a 1 in 16 chance of being a code word in the binary Hamming 1511 code. So I will emphasize it's pretty important to memorize the theory behind here, because a question could come like this, and it's going to depend on the property of the Hamming codes and the intuition behind why we have the dependent columns as information bits and the independent columns as check bits, right? So going to this question, we note that random string of 15 ones and zeros, those information bits could be anything, but we are more interested in the check bits, right? Because they have to be fixed. For the 1511 Hamming code, we have our length of 15 and we have 11 information bits, which means we have 15 minus 11 check bits. Now, if we were kind of to brute force, right, because we have a random string, we want to see out of those 4 check bits, there must be a unique encoding for the other 11 information bits, right? So there is a 1 in 2 chance we get a check bit correct, right? And some basic probability, all of these events together. So there are 4 check bits that we want to get right to be a valid binary Hamming 1511 code word. Will just be this to the power 4, which is 1 to the 16. Yep, so I guess it asks us to check whether this is true, and yeah, it's true. Yep. And since we're working in binary, there's only a possibility of it being 1 or 0, so there is a 1 in 2 chance of us getting it right. I suppose if we're working in a different radix, R, the probability would be 1 over R. And this is what the 1511 Hamming code looks like. See that this is a bit of a different way we've organized the check parity matrix, and we can see all the leading columns are going to be on the right here. A final remark for binary Hamming codes as well. See, these are all valid binary Hamming codes, right? So this is going to be our N, and this is going to be our K. Okay, and this is our length, right? because remember we have binary Hamming codes of NK. This R here is going to be the ratio of information bits to length, right? So this is going to be like the transmission ratio, I think. And you can see here, as we get longer codes, we can transmit more bits. But as I stated before, a binary Hamming code can only correct one error. And you probably can see that if we have a longer code word, there's a higher probability of error. So it makes sense for long words that the binary Hamming code isn't that useful, as we only correct one error. Moving on, Hamming distances and weights. Okay, so what is a Hamming distance? So the distance between a code word X and a code word Y is simply going to be the number of bits in X and Y that differ, right? So the way you would determine this is if we had something that looked like this. You'll see, you'll just go pairwise across all of the elements in the two code words. So this is like X and Y. You see, okay, that's different. That's different. This is the same. This is different. This is different. So since there are 4 bits that differ between the code words, the distance is going to be 4. Going off this definition, then for a set of code words C, the minimum distance of C is going to be the smallest distance between any 2 code words. In just a bit of rigorous definition, the code words can't be the same, because obviously then the distance would be 0. Hamming weight, however, is going to be defined off distance, and it's just going to be the number of 1s in a code word, or the distance between the code word and 0. So if I had a code word 10110, there are 3 1s, so the weight is 3. And similarly, the minimum weight is defined as going to be the smallest weight in the set of code words C. If we denote D as the minimum distance in a set of code words C, then we can develop an error correction strategy called minimum distance decoding. And this would be similar to what we talked about before for the repetition code. Yeah, as said before, if we have 2t plus 1 or 2t plus 2 fixed length codes, we can correct up to t errors. Yeah, so a final exam question. Bit of a doozy. I think this is 2018. Final 3, part 4. We have an error correcting code C defined for integers n is greater or equal to 3. And each message is going to consist of a block of n minus 1 to the power of 3 integers, right? So it kind of says n has to be greater or equal to 3. So this could be at most 2 by 2 by 2 integers, right? And if you see what it's hinting to here, it's going to be cubic array. So 3-dimensional, right? So we're saying that, we can have a message smallest 2 by 2 by 2 cube. And we also get an additional layer of check bits. So the smallest cube we can have is 3 by 3 by 3. We have a syndrome here, which is just stating the sum of each layers in all the different axes, right? Have to have a parity of 0. So you can see here, we use the variable s here, and we move it in different positions to represent the way we go through the different axes. Here's an example of what that would look like. So this is a way you can represent a cube with the 3 different layers. And if we add all the elements in each layer, they should be equal to 0. And also, if we go through the different axes, so for example, adding all these elements, then these should all be equal to 0. First question is going to be, why is the code C 2 error correcting? So I will use a 2-dimensional analogy first before we extend to the 3-dimensional case. This is going to be similar to the burst 8-bit ASCII burst code. So if we had a bunch of numbers here, let me just write out some valid codes. 1, 1, 1, 1. We can see here that if we have an error, we can go through the parity, just like how we have a parity check for this question, and be able to, detect where an error is, right? And we can fix that. However, if we had two errors, so for example, this also got flipped, we would be able to detect two errors here, but we wouldn't be able to tell where they are. Additionally, if we keep going up the cases, let's say we have 4 errors, right? So I've now swapped all of these bits. And if we calculate the parity again, oh, something interesting. Now we aren't able to detect those errors, right? So using those two cases of seeing okay, when can we correct, when can we only detect, and when can we not detect at all, we can answer the two questions. So A, explain why the code is two error correcting. So I'll have to describe this, I think, because it might be a bit horrible if I try to draw this three-dimensionally. But you can imagine if we have a cube of bits and we have two errors, there's going to be at least one layer in one of the axes, right? So it could be through this axis, or maybe through this vertical one here, or this sideways one. There will always be at least one axis that has only one error in it. And we can see if there's only one error in a row, then we will be able to detect that. So in this case, our layers are just going to be one-dimensional, right? But as we extend to the three-dimensional case, we have 2D layers. So that is why the code C is two error correcting. But as you saw before, if we have a box where all of the errors have occurred, we can't detect anymore, right? And for the three-dimensional case, if we had a cube of bits and they all got flipped, the parity for each layer in each axis will be unchanged, right? So if I take this layer at the top, 1 plus 1 plus 1 plus 1, still going to be 0. So the question asks us, what's the maximal value of t for which C can always detect up to t errors? It's going to be the same question as find t plus 1 for which we can't detect t plus 1 errors, right? And using the three-dimensional analogy, this t plus 1 is going to be 8. So if we have 8 errors, we can't detect any of them. So therefore, if t plus 1 is equal to 8, makes sense that t equals 7 is going to be the maximal value of t for which we can correct t errors. Okay, does that all make sense? Great. Going on to sphere packing. So a t error correcting radix R code, or C, of length n, which has minimum distance d equals 2t plus 1 or 2t plus 2, right? So just the odd or even case. Then we have this inequality, which states that the number of code words, so this number of code words here, C, will satisfy this inequality. Great. Okay, what does this mean, right? So Rn, we can think of it as the group of numbers. So the all possibility amount of kind of binary words that we can form with our code alphabet, right? And we can think of the code words C is going to be these dots that are scattered around R to the N, right? But what is this? So a bit of combinatorics here, but this term is going to represent the amount of words that are around these code words, right? So you can think of it as circles around the word. Right? And we state that it's T error correcting. So what it means is that for any other word that exists in a circle, we can correct it to the code word there. And we state the inequality just means that the corrections to the code words all must fit in R to the N. Great. Okay, moving on to binary linear codes. So this is essentially a generalization of the Hamming codes that we had before. It's now going to be m by n, any binary matrix of rank m. It's important, over the binary field. Then we treat H as a parity check matrix before, and we have the same syndrome. Great. And we now state a theorem. The minimum distance d of a linear code with a parity check matrix is going to be the smallest integer r for where there are r linearly dependent columns of H, which is great and will aid us. So for example, if we have a binary linear code with a parity check matrix like this, and we receive this message, how can we correct the encoded message and determine what the information was, right? So first of all, going off what we said here, we got to make sure we were able to correct the encoded message. If we remember before, d is equal to 2t plus 1 or 2t plus 2, depending on the parity of d, of course. And that's going to determine t, which is the amount of errors we can correct. So if we have a matrix like this, we can see that we have leading terms in these columns, but a fifth column, right? Intuitively, okay, it kind of implies that the fifth column can be formed by some kind of linear combination of the first four columns. And actually, if you just add up the first four columns, right, you get the fifth column. So it makes sense that the smallest integer r, for where there are linearly dependent columns, is r is equal to 5. And by this theorem, d is also equal to r. So d is equal to 5 is equal to 2t plus 1. So it makes sense that t is equal to 2. So we know, at the very least, we've justified, if we correct this message, we can correct, at most, 2 bits. So first of all, we need to multiply the check parity matrix by our message first to validate if it's a correct message or not using the syndrome. So if we multiply it out, make sure we take the transpose of our message as well. 1, 0, 0, 0. Yep. By our message. If we go element-wise, we should be able to have the vector 0, 0, 0, 1, mod 2. And unfortunately, you can see that this isn't going to be equal to any of the columns in our check parity matrix, right? Unlike the binary Hamming code. But we know we can actually correct 2 errors here, unlike the binary Hamming code, which can only correct 1 error. And we see that our message, or the syndrome of our message, is going to be the sum of the first and last column, right? So it's equal to 100 plus 1001. And these are going to represent the 2 errors that we can correct, right? So since this was H1 plus H5, we know that the first and fifth bit were actually an error. and we can correct those and retrieve our information. So all of them are 0, and the information is 0. In this case as well, I believe the independent columns are going to represent our check bits. So it's just the last column 0. That is our message. Okay, so we have a binary linear code C that has another parity check matrix. And we have a code word that's transmitted through a noisy channel, in which each bit xi is corrupted with equal and independent probability p. So A, find the probability that all errors are corrected correctly when using the minimum distance decoding strategy, right? So there are 4 places where we can have an error, and also there will be a probability we don't have an error, right? And then we have to do this 4 times. So this is going to be our answer for 4. Also note that the smallest set of columns that are linearly dependent is 4, right? So this is going to be the amount of errors that we can correct. For part B, we're asking, find the probability of detecting at least one error when using the pure error detecting strategy, right? So if we weren't correcting and we were just detecting, this is going to be equal to the probability that we find one error plus the probability we find 2 errors plus the probability we find 3 errors, right? Or conversely as well, this will be 1 minus the probability we have 0 errors. And make sure as well, we factor in the probability we have 4 errors, right? As we have code words of length 4, we can't have more than, we can't have more than 4 errors, right? So using some simple combinatorics as well, the answer here is going to be, if we have 1 minus p, 0 errors, minus probability of 4 errors. As this has less terms, I believe it's simpler. It will be 1 minus 1p of 4, because it's probability we have 0 errors, minus the probability we have 4 errors. Great. Yep. Or the other method as well, which is valid. Okay, moving on. Generator matrices. So this is a different way we can think about how a set of code words are defined as opposed to a check parity matrix. So if we let B be the basis for the set of code words C, and let G be a matrix where all its rows are the vectors in B, then the generator matrix consists of rows which represent the elements in the basis B, right? So if we have code words, I believe 0, 0, if we have C be defined by, if we let, the basis B of a set of code words C be equal to 1, 0, 1, 1, and 0, 1, 0, 1, right? A generator matrix could look like, let me write this down here. Generator matrix could look like 1, 0, 1, 1. So that's going to be our first basis vector, and 0, 1, 0, 1. Okay, so a standard form parity check matrix. So we're now building off the generator matrix definition. So if we suppose that H is the parity check matrix for a certain set of code words C, then we can row reduce H, as we might have seen for the 1511 binary Hamming code before. We can permute columns of the matrix using row echelon matrix valid operations. And we can have the first few columns form an identity matrix. So identity matrix is going to look like this, where the diagonals are going to all be 1s and the rest are 0s, right? And the rest of the matrix will be basis B. So it's going to be an m by k matrix, which represent the basis vectors, but as column vectors. So if we were to now transform, given a standard form check matrix of the form of the identity matrix followed by the basis as column vectors, we can transform it into a generator matrix by taking the transpose of the basis matrix, because the generator matrix has it as row vectors, and then also filling in the rest with an identity matrix. So going what we said before, we have a parity check matrix of this form. H is equal to identity matrix and the basis. And if we kind of draw that line between the two matrices, we can see that, okay, G is going to be the transpose. So that's 1, 1, 0, and 0, 1, 1. And then we will just fill in the rest with an identity matrix of size k. So we have k rows here, so it will just be identity matrix of size 2. And then now we can see the, B here was just a matrix, not the basis column vectors. But now the basis can be retrieved here. From the generator matrix, we have 1, 1, 0, 1, 0, and 0, 1, 1, 0, 1. Great. Additionally, let's talk about extending binary linear codes to a higher radii. So we can see the ternary Hamming code, which are in the lecture notes. So we have the column vectors as defined before, increasing in value. And we can see here how we'd extend this type of code. Now we have more complex entries besides 0 and 1. So for higher radii, you would have, I guess for a ternary code, you could have 2 as a valid value, or up to like n minus 1 for radix n. But we can see some things break here as well. After calculating the syndrome, it's now difficult to now identify which linear combinations form the syndrome. So as we did before as well, we were able to just look by inspection and see that our syndrome was equal to 2 columns here together. But as we have a high radix, there's more possibilities and it's harder to do so. And additionally, when converting from H to G, we have to take the negative of the B matrix transpose, because when we were doing the binary case, we could ignore that because minus 1 is equal to congruent to 1 in binary. Great. I think that is it for topic 2. And Matthew, I think, should we take a little break? Sure. Yes. Yeah, sweet. And then we'll move on to compression coding. I was actually thinking something fast. All right, great. Sweet.
Thank you. I call that matrix the basis column vectors, but I guess it's just like a misuse of notation calling that B. But I think that's taken from like the lectures though. Because when you have it in the standard form check parity matrix, you know, you have the identity matrix and then a matrix B. But those column vectors aren't the elements of the basis. But they still use B as the notation. Because you have to add on just extend it by the little identity matrix at the end. And then it becomes the basis elements. So it's related, but
All right. Hello. Welcome to part 3 of the workshop. We're going to be starting off with compression coding. Can I just get a check that I don't go too loud, just on the audio? All right.
I think as long as it's not peaking here.
Right, okay. I'll try to be as a little bit further away then. All right, so let's start off with compression coding. So a lot of slides. The only thing that you really need to know from these slides is that the idea for compression coding is pretty much that we want to encode, getting used to the laptop, to the pen. The idea is that we want to encode more frequent source symbols with shorter code words. This is kind of like the motto for this part of the course. And it's something that we will come back to a lot as we go through questions. All right. So also this part of the course, this part of the revision seminar, we're going to be using these symbols, this convention, where we're going to say S is going to be the set of symbols from the set of source symbols from S1 to SQ. The set of code words is going to be C1 to CQ, P1 to PQ, and L1 to LQ. These are the things that we're going to be using in this section of the course. All right, couple definitions. I'll go down to the full definition. All right, so a code is uniquely decodable if there is only one way to decode any encoded message. Right, that's probably something that you want in a code, is for you to be able to decode it. The other thing is it's instantaneous if no code word is a prefix of another, right? That just makes it really easy to decode. Right, let's see an example of that. So the first example in this section is the standard comma code. And the standard comma code is basically just we use the code words 0, 10, 110, and 111, right? So we have our choice of code words for source symbols, and we are choosing 0, 10, 110, and 111. That's just because this is an instantaneous code, and it's also uniquely decodable. Right, so this is just kind of our prototypical example of an instantaneous, uniquely decodable code. The way that we can tell that this is instantaneous is that no code word is a prefix of another, right? So 0 is not a prefix of 10, is not a prefix of 110, is not a prefix of 111. Cool. What about this code? Well, is it instantaneous? I'm going to say the answer is no, because S1 is a prefix of S3. Is it uniquely decodable? That's an interesting question. It turns out it is not uniquely decodable. And the way that we show that it's not uniquely decodable is to find a counterexample. So I'm going to use the counterexample 0, 1, 1, 0. Now, if I look at this counterexample and I read it, I am figuring out how to use the pen, so I'm left-handed. So we can have this as S1, and this, not S1, this would be S3, and this as S1. Or we could read it in a different way, where it starts off with S1 and then ends with S2, right? These are the two ways that we can show that it's not uniquely decodable, because we can find two ways to decode it. That's what we say there. Here's another code. Is this one instantaneous? I say the answer is, well, no, it's not. For the same reason as before, right? 0 is actually a prefix for every single one of these codes. Yeah, actually this is picking a little bit. So, what about this other one? What about uniquely decodable? Is it uniquely decodable? Well, I actually claim that it is uniquely decodable. And it's uniquely decodable because I can write it backwards, and it becomes the standard comma code. So I could write 0, 10, 110, and this is just the beginnings of our standard comma code. So it's uniquely decodable because I can find a reversible mapping between the standard code and this code. All right, let's move on. This is what is said there. That's what is said there. Oh, hey, here's a cool takeaway. When we look at instantaneous and uniquely decodable codes, instantaneous codes are actually a subset of uniquely decodable codes. So every instantaneous code is uniquely decodable, but not every uniquely decodable code is instantaneous. And that's exactly what we saw here, right? It was uniquely decodable, but it was not instantaneous. All right, decoding an instantaneous code is really simple. So we have, this is an instantaneous code, and we want to decode it. So the way that we're going to do that is we're going to read left to right, and whenever we see a code word, we're going to stop and write down the source symbol for that code word. Okay? So I am just going to do this by crossing out. So I cross out, I look at 0, it's not a code word. I move to the left, I move to the right, and 0, 0 is a code word. So I can cross that out and write C2, which I guess is S2. Yeah? I can now continue, and I have 1. Can cross that out, and that because that is S1. 0 is not a code word. 0, 1 is a code word. That's S3. 0, 1 again is a code word. That's S3. 0, 0 is a code word. That's S2. 1 is a code word. That's S1. So our answer is going to be S2, S1, S3, S3, S2, and S1. Right? Right. Very cool. Makes sense. Makes sense. Going down 0. Did I get that right? 2, 1, 3, 3, 2, 1. 2, 1, 3, 3. Hey, I got it right. Let's go. All right. Kraft-Macmillan theorem. So this is probably one of the first theorems in this part of the course, and it's a pretty cool theorem. Thomas Britz does make a lot of recommendations about like, hey, what do you need to know the proof for? There's this like whole document on the Moodle, and he does recommend that you know the proof for most of the theorems that we're going to go through for this part, which is, you know, kind of but yeah, it is what it is. I don't think we have time to go through all of them today. I might give a quick run through of them if we finish early. I can go back and give a run through of these. But it is what it is. Anyway, let's actually talk about this theorem. It's been on the screen for a little bit. It says that, hey, let's say we have some set of lengths that we want to be code word lengths. Then the following statements are completely equivalent. We can say that there is a radix R, uniquely decodable code, with code word lengths L1 up to LQ. There is a radix R I code with lengths L1 to LQ, right? So these two statements are about like existence, yeah? They're saying there exists. And we're saying that the existence is exactly equivalent to this statement being true, right? This is like kind of the bread and butter of the Kraft-Macmillan theorem. Very loosely, what this statement says is that our tree diagram has to be less than full, right? So I guess I'll give like a quick example. Let's say we were dealing with a radix 2 code, right? And we wanted to have 3 code words, all of length 1. Well, how this sum will look like is it's going to look like 1 on 2 times plus 1 on 2 plus 1 on 2 all to the power 1, yeah? And that's going to equal 3 on 2, which is over 4. So there exists no radix 2 code where you have 3 code words of length 1. Right, hope that makes sense. Feel free to put stuff in the chat, and hopefully someone will be able to tell me if there are any questions. Cool. Here's another example, something that might be a little bit more typical of what you might have seen in the exams. you can use this, I guess you'd call it the Kraft-Macmillan sum, to figure out that 1, 2, 3, 3, 3 is not valid as a radix 2 code. Cool. Here's just another quick example. So this one is what we've just been doing, but there is an extra step, which is, can we construct such a standard instant code? Right, so I guess I'll just do the sum, just, for completeness. This is going to be 1 on 3 to the power 1 plus 1 on 3 plus 1 on 9 plus, I'm going to just say 4 on 27. Hope you'll let me do that. And this is going to equal, I can not do the arithmetic, but I know the answer because I have practiced, is going to be 25 on 27. Right, so this is less than 1. And we see that this code can exist. Cool, so let's construct a standard I code. So there are 2 ways of doing this, and I'm going to show you one way, and then the slides will talk about the second way. And the way I'm going to do it is I'm going to construct a tree diagram. And, well, each node of my tree is going to have 3 legs, and these are going to represent 0, 1, and 2, because we're in radix 3. And I'm just going to go down my tree and fill in as many code words as I can with each length before extending the tree to the next. So this is going to be S1. This is, that is a blip. This is going to be S2. And that's our 2 code words of length 1. Now we want to go to length 2, so I'm going to just extend this, 0, 1, 2. This is going to be like going from top to bottom. We need a code word of length 2, so that's going to be S3. Now we're going to need 4 code words of length 3. So what I'm going to do is I'm just going to take our 3 from this code. So this is going to be S4, S5, S6. And then, I have to go back down the tree, go to this last one. So we have 0, 0, 1, 2. And this is going to be S7. Right, so again, for completeness, I can write down S3, S4, S5, S6, and S7 just by going down this tree. So this was 0, this was 1, this was 2, 0, this was 2, 1, 0, this was 2, 1, 1, this was 2, 1, 2, and this was 2, 2, 0. All right, hopefully that's correct. We go down, we see the answers. Hey, well, I got the last one right, so I'm guessing that we're good. All right, next thing is minimal codes. So minimal codes are kind of like the whole point of compression codes is to find minimal codes. So when we think of compression, we think of making codes as small as possible, all in the name of efficiency. And yeah, so the thing with minimal codes is that there is this idea of an average length, right? So here is just a formula for the average length, and here's a formula for the variance. The variance doesn't show up quite as much, but I guess it's just good to have here for your culture if you end up doing 2801. This is, you know what, I'll just do a little bit of an extension for those people. You can write this with the notation E of L, and then this will be E of L squared minus E of L squared. Don't worry if that makes no sense to you. It's just a little bit of a extension. Yeah, is there anything else to say about these? I don't think so. This is just the weighted average is how we define the average length in this course. Cool. Yeah, and if the average length is minimal, then we say that the code is minimal, right? We say minimal with respect to the probabilities P1 to PQ technically, but usually we just say it's a minimal code. All right, so here's an example of what's definitely not a minimal code. So if you remember up to like the beginning of my part of the course, my part of these notes, is that I said that what we want to do is we want to put minimal probabilities, we want to put the shortest code words with the highest probabilities or something like that. And well, this definitely does not do that because we're putting code word of length 3 with the highest probability, which definitely won't make a minimal code. All right, so this is going to be 2/3 time, what am I doing? So we see that this is equal to 5 on 2. I'm going to suggest that we could actually do better. If we said that L was equal, we set the code words equal to, like, let's say like the standard comma code, we could have 0, 0, 1, and 1, 1 be our codes. And in that case, we'd have 2/3 times 1 plus 1/6 times 2 plus 1/6 times 2, which would equal, and you can check this, is 4/3, which is less than 5 on 2. So we have found a counterexample, and we can say that this code is not minimal.
Is minimal code only defined by its like better than
Yeah, so that's true. Yeah, so the question was like, yeah, so the question was for the people at home, is a minimal code just defined by it being the minimal possible assignment? And the answer is yeah, pretty much. We just assign the code to the set of source symbols such that the length of the code is as small as possible. We'll see a lot more about that in the information theory part of the course, where we get to talk about like entropy and stuff like that. All right, hey, we see exactly what I just did here, maybe written out in words. So if something was unclear, you can just check the slides. All right, from this point of the course, we're going to be looking at decreasing probabilities, or at least non-increasing. That kind of makes sense. Going back to our motto, I'm actually just going to scroll up to the motto. This part of the course is, where was it? It was, the idea is to encode more frequent source symbols with shorter code words. That was the big idea of this part of the course. And so we're just going to be assuming that our code words yeah. All right, so here's a theorem for minimal codes. This is also something that I think Thomas Britz wants you to know the proof of. I think the proof of this one is fine-ish, I guess. Anyway, so if we have a uniquely decodable code with minimal average length, so we're assuming, okay, we have a uniquely decodable minimal code with respect to its probabilities, then after maybe shuffling around code words of equally likely symbols, the length is going to be shortest at the beginning, and it's going to end being longest. That kind of makes sense. If the probability over here is we want to pair the largest probability with the shortest code word, so this makes sense. All right, we have something else. LQ minus 1 equals LQ. That kind of like at least is consistent with what we had before, yeah? So we had 0, 1, 0, 1, 1, 0, 1, 1, 1 was our standard comma code. We see that the length of the last two is the same. You can think of that maybe as you're always going to be able to look at the last digit and commute it around to all of its possible values in the radix, yeah? If C is instantaneous, then C of Q minus 1 and C of Q differ only in their last place. That also kind of makes sense just by looking at this standard comma code. And then if C is binary, then we have that the Kraft-Macmillan sum is equal to 1. Right, so I guess this is just saying, hey, if we have a uniquely decodable code that is minimal, then we have all of these properties are true. We also kind of see this is going to be true when we look at Huffman, that Huffman algorithm. Yeah, here's just an example. You can go through this at home and just verify that all of these statements are true for this code. Yeah. All right, Huffman's algorithm. So we're getting to the part of the course where it's literally just going to be examples, 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 examples as I go through different kinds of algorithms. Huffman's algorithm, let's go down to the full definition. And you can look at this you can look at this slide, and if you can read it, you're more patient than me. The way that we're going to do this in this revision seminar is we're just going to go through an example. But if you really want to read it, it's there. So let's use Huffman's algorithm to construct an instantaneous minimal code for this source, where the probabilities are 0.4, 0.3, 0.2, and 0.1. All right, so the way we're going to do this is we're just going to do our Huffman diagram, our Huffman algorithm. We've done this a lot of times in the tests, so hopefully this isn't too new to you. What I'm going to do is I'm going to take these last, we're in radix 2. The reason we're in radix 2 is because it doesn't state otherwise. That's true. Yeah. I guess the Huffman algorithm is also like defined as radix 2, and then we modify it to be radix 3 after. But yeah, this is just like a true thing about the world. The way we do it is we take the bottom R symbols and combine them, oh, that's wrong, into a single source symbol. And the way I do it is I put that source symbol at the very top, and that ensures that the algorithm is going to work properly. 0.4. And what I'm going to do is I'm just going to draw a couple dotted lines. Yeah, and then we repeat. So I take the bottom R, so in this case it's bottom 2, I combine them into one symbol, 0.6, I circle it. That'll be useful when we do Knuth's theorem. And then I just draw some legs. Do it one last time to get 1. The end, 0, 1. Cool. So I guess to complete this question, we have to now look at our tree and figure out what the code words are. So we have S1, S2, S3, and S4 to get. What is it? Well, we just follow the tree down. So this was S1, blah, 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 blah. It's a 1. S2, we can follow the tree down. Oh, it was a 0 and a 1. S3 was a 0, 0, 0. And S4 was 0, 0, 1. All right. And that's how we do a Huffman algorithm, radix 2. Here's a neater diagram, I guess. And hey, we got it right. Hey, here's another big thing. Knuth's theorem. Knuth's theorem, I'm actually not sure if it's pronounced Knuth or Knuth. I'm just going to say Knuth. It says that the average code word length, I write the average code word length like that because I'm a physics student and I am stuck in my ways, is going to be the sum of all of the values that we circled. Right, so this is 0.3 plus 0.6 plus 1.0. Cool. That's just what Knuth's theorem says. It's just a, I guess we call this the things we circled child nodes. That's cool, I guess. Yeah, going through this, radix R. It's very similar to what we were doing before, where we had radix 2. But in this case, we actually have to add dummy symbols such that the number of symbols that we have is equal to 1 mod R minus 1. This is kind of pretty easy to see. Let's say we had some set of source symbols. And now at the next step in our algorithm, we're going to have less symbols. And how many less symbols are we going to have? Well, we take our symbols, combine them into one symbol. So we're going to lose R minus 1 symbols at every step. If we have to end with a 1 at the very end, then we had better hope that we have 1 more than a multiple of R minus 1 symbols. Right? So this is a radix 3. We won't go through this. We will just look at the solution because it's very much the same thing as what we did before. We take 3 variables, combine them into 1, and draw our legs. Yep, continue doing that, and you will be able to do radix 3, and maybe even radix 4 Huffman algorithms, depending on how nasty the exam is. All right, extensions. So, next bit is this idea of an extension is basically, there's a really nice there's something really nice that's said here, which is, where is it said? Basically, the idea with extensions is to encode multiple symbols at a time, right? Encode multiple symbols at a time instead of just one. So you can imagine that if we want to compress some kind of code, let's say we had only two source symbols, S1 and S2, and we have to give code words to these source symbols. Well, the shortest code words that we can give them are 0 and 1. So the average code word length for our codes is just 1, right? Like no matter what S1, S2 are, it's just going to be 1. But we can do better than that. And the reason that we can do better than that is with using extensions. The way that extensions work is, let's say we had some message, M, and it was like S1, S2, S1, S1, S2, S2. What we do is we assign code words to pairs or maybe even triples of words. So we maybe have a code word for this one, and maybe we have a code word for this one. And on average, per symbol, the length of the code words is going to decrease.
There's a question in chat.
Yeah.
How do we know if the tree points to a 0 and 1? Can't we technically have there was some like symbol and encodings? I think it's for the
Can you show me that question real quick? Can you just like bring up the question over here? Yeah.
Wait, do you have
I don't have the feed on my.
yeah, sure.
So the question is, how do we know that the tree points to a 0 and 1? Can't we technically have S1 equals 0, S2 equals, or is it convention for the small? So yeah, it is convention for the smaller number to be at the top. Yeah, this is for Huffman. So I'm looking at binary Huffman. How do we know that the tree points to a 0 and 1? Yeah, so it's literally just convention. So if I had a look at my proof that I had before, yeah, you're saying, hey, we could have S1 is 0, S2 is 10, S3 is 111, and S4 is 110. That would just be exactly equivalent to S1 equal to 0. Yeah, so what we're doing is we're just changing all of our zeros to ones. It makes no difference at the end of the day. All you're doing is you're just defining what you want to be your 0 symbol and what you want to be your 1 symbol. Yeah. You could technically do that. I think the convention in this course, though, is that we have zeros on the top and ones on the bottom. Yeah, you will be marked against the convention. So that it's probably something to, yeah, it's something that you're just going to have to know and do. All right, let's go down. I had a look at this. I've done radix R. I'm looking at extensions now. I went down here. Yeah, cool. All right, so here's a definition of an extension. An extension for probabilities blur of the nth extension is written as this. It's the Cartesian product containing all strings of n symbols in S. The probability of each symbol is just the product of the probabilities of the constituent symbols. And we also order the new symbols in non-increasing probability, right? So that means we start off with the biggest and it goes down. Yeah, very, very natural. All right, is this? Yeah, so here's just an example. We'll go down to the bottom so we can just look at the whole example. So consider a source SAB with probabilities 0.3, 0.7, and 0.3. Then S2, this is all the elements in S2, right? You can think of that as we're writing down all of the possibilities pairwise. And it has probabilities 0.49, 0.21, 0.21, 0.09. Right? If we run Huffman's algorithm on S2, so that would be like running it on 0.49, 0.21, 0.21, 0.09, right? Just running it on this. We will see that the average length is 1.81, which is good. It's better than what we would have had if we were just putting one code word each source symbol. Each symbol S2 is made up of 2, yep. And so per source symbol, we are going to have 0.9. Yep, cool. Makes sense, makes sense. There's just a duplicate slide for some reason. Markov sources. Hey, this is a pretty cool part of the course. Let's go down to the full definition. And then, maybe not. We'll start off over here. All right, so far we've been looking at sources where we have been let me just state what's on the slides instead of trying to make up my own stuff. All right, so far we were able to take advantage of source symbol probabilities in order to reduce the average length of code words. In fact, given yet more information about the source, we can do even better compression. Right? I kind of hope that would be true. If we gained more information about the source and we somehow made code words that were longer, maybe we just shouldn't have learned that information. All right, so a Markov source is a source where the probability of a symbol depends on the symbol before. So you might have like a message that's like S1, S2, S3, S1, 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 S1. And maybe in this case, S3 will always appear after S2, but if there's an S1, you can never have an S3, or something like that. Basically, the probabilities of the source symbol showing up is dependent on what source symbol showed up before. Right. The way we write down this Markov source is we place all the probabilities together in this thing called a transition matrix. The ith column of M shows the probabilities of each. So I'm just going to write this down. We have M is going to be, let's say this is the probability of S1 given S1. This is the probability of S2 given S1. This is the probability of S3 given S1. And, well, this one would be the probability of S1 given S2. And that's all I'm going to write out. It continues. Yep, so this is what our Markov transition matrix looks like. And we see that the columns of M show the probabilities of each symbol occurring right after SI. Cool. Additionally, we have this vector called the equilibrium. So the thing about the equilibrium, and based on past exams, this is probably going to show up, is that the if I draw MP is equal to P, right? So P is an eigenvector with eigenvalue 1. That's shown up in like literally every past paper for the past 3 years, or from 2016 through 2019. I looked at those past papers, and every single one had something where you had to like verify if a equilibrium was actually the equilibrium. And the way you do that is you look at this and you verify that it's an eigenvector just by multiplying. All right, here's some exam tips for you. All right, so something else about P is that it's actually equal to the probabilities of S1, S2, and S3 showing up in the first case. So that'll make more sense if I put it into the context of a message. So we have a message, and it can either start with an S1, it could start with an S2, and it could start with an S3. And the equilibrium vector is the probabilities that the message starts with S1, S2, or S3. Cool. Here is a Markov source with an equilibrium vector. Yeah, we've gone through kind of like going through this. I guess maybe I'll just like label these. This is the probability of S1 given S1, and this is maybe the probability of S1 is how I'd write that. Cool. Combined with the coefficient at the front. Cool. So yeah. Let's have a look at this other thing. This next slide of slides is talking about the Markov length. So the Markov length is just is a weighted sum of the length of the Huffman codes for the columns, right? So this is way easier to see with an example, but maybe we'll just like talk through this slide first. So Turns out we can take advantage of Markov sources, let S1 through SQ be Markov source with transition matrix M and equilibrium P. Then Huff, I guess we'll call it Huffman E, or Huff E, is the binary Huffman algorithm applied to the vector P. So above, this would just be applying the, let's say we had like 0.1, 0.4, 0.5, then we would apply the Huffman algorithm onto those probabilities. And that would be Huff E. And Huff I is just applying the Huffman algorithm onto the columns of our transition matrix. Right, this is way, way, way easier to see with an example. It's also, we're going to do some coding after, but let's just start with an example. So here, what do we have? I'm going to use a different color, and I'm going to make it smaller because I need to actually go zoom in a little bit. So I am actually going to calculate the Huffman algorithm for each and every one of these, just because I think it is good to do. So Huff 1 is going to be 0.6, 0.6, 0.2, or maybe I'll only do 1, 0.2. This is going to go to 0.6, 0.4. This is going to go to 1.0. And so we get Huff 1, Huff 2 is going to be, I'm going to look at this. I'm going to make this a little fatter because 0.4, 0.4, 0.2, 0.6, 0.4, 1.0. Then we have Huff 3, which is just going to be, 0.6, 0.2, 0.2. This is going to be 0.6. Oh, I have to write, because this is not in order, this is S2. This is S1. This is S3. Because I have to reorder them for the Huffman algorithm, yeah? This is 0.4, this is 1.0, and then Huff E is just going to be, if you will permit me to just ignore the 1 on 20 and just write this, then Huff E is going to go, oh, I've run out of space, but it's going to go 11, 9, 20 with this as the legs. All right, so that was just going through this. And we see the exact thing here. The question here is asking for us to find the length of the Markov source. So the way we're going to do that is, well, we have Knuth's lemma, which was stating that we can just sum up these circled probabilities. So this would be 1.4. This would be 1.6. This is also going to be 1.4. And we weight them with the probabilities of our equilibrium. So we're going to have the length of the Markov length is going to be 9 on 20 times 1.4 plus 7 on 20 times 1.6 plus 4 on 20 times 1.4. All right, so that's Markov length. The next bit of this question is asking for us to encode and decode. So what's all this about? Well, I'm going to just scroll down here. They're talking about the equilibrium lengths and the Markov lengths and all this. This is where we're going to encode and decode. So the way that we encode using a Markov source is that the first letter is encoded with Huff E, and then depending on which source value it was, we swap over to the next Huffman algorithm and just keep on going left to right, doing that exact same process. So it's way better to see with an example. So what we're going to do is we're going to encode Huff S2 with Huff E because it's the beginning. We're going to have 0, 0. We move on to S1. The last one was S2, so we're going to encode S1 with Huff 2. S1 is going to be 1, so we have 1. The last one was 1, so we have to encode S1 with Huff 1, that's 0. The last one was 1, so we have to encode S3 with Huff 1, which is going to be 1, 1, 1, I believe. I hope that's right. Huff that. Yeah, we're right. Okay. the next bit is we're looking to decode. And so this is actually kind of similar. To decode this, we're just going to start off with huff E, find what its decode is, and then we're going to switch over to that next Huffman code. So again, a lot easier to see with an example. Hey, we've already done something for the slides have done something for us. 0.1 goes to S3. So we immediately have our message is going to have an S3, and it crosses off those two. Then we continue reading, this time in huff 3, until we see a code word. 1.1's a code word in huff 3, so we get, again, S3. Well, we just got S3, so we want to continue in huff 3. And, well, we just continue until we see a code word. Hey, C2 is a code word, so our message is going to have an S2 in it. Now, because we just have an S2, we have to go over to huff 2 and continue reading. This is going to turn out to be S1 and S1 if we continue to go through this. Yeah, because I just went over to here and I did this and then. Yep, so that's how you decode a Huffman message. Cool. We are kind of running out of time and there's still a couple messages to go through. Here is a past paper question. We're not going to go through it because it's very much the same thing as what we did before, but I will talk you through the strategy. Huffman, find the appropriate Huffman code for the Markov source. Huffman codes, so this is when you're calculating, so step for A, you want to calculate huff 1, huff 2, huff 3. Then you want to decode, so you're also going to want huff E. And then with all of these codes that you have, this part C is saying, hey, using the Huffman code from part A, suppose that a message M is encoded as 3 bits and exactly one of which is 1. So let's just write out all the possible messages. You could have 001, 010, or 100, and you just have to decode these and find the possible messages. A lot of these won't be decodable, so yeah. Anyway, that's what that is. All right, so let's get on to arithmetic coding. Arithmetic coding is like kind of the most annoying bit of this course because it's arithmetic and it's so easy to make mistakes. Let's talk about like what the idea of arithmetic coding is. We are going to encode a message onto the real number line between 0 and 1, right? So we are going to be given a set of symbols, let's say S1, S2, S3, and a stop symbol with corresponding probabilities. We are going to split the interval 0 and 1 into subintervals with length being those probabilities. And then our message is going to, and then that'll be the first part of our message, and then we will continue to subdivide intervals. Again, kind of hard to explain, way better to see an example. All right, just going to stop here in case anyone wants to pause the recording and have a look at what the actual definition is. But let's do an example. So, so let's consider this source with probabilities blah, 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 blah. We want to encode CAB stop. So the best way to go about this question is to write out this table. Right, you're going to start off with the letter. So I want to have C, I want to have CA, I want to have CAB, and then I want to have CAB stop. This is what I'm going to build up. I'm going to build up these messages. 2 bits of information that are important is you want to have the start of your subinterval and you want to have the width of your subinterval. We're going to be able to use these two to be able to like generate the encryption. So C. It's also really good to have the just a little picture telling you where A, B, and C are. So we split up our interval so that this bit is A, and that's at 0.2. B is a length of 0.4, so it goes to 0.6. C is 0.1. Oh, you can tell I've done that to scale. 0.7. And then stop goes to 1. All right, so let's just go through this example. So C, where does C start off at? C starts at 0.6 and it has a width of 0.1. hey, we've got the first entry in our table. CA is going to have 0.6 plus, well, it's actually going to be 0 times 0.1. We'll see that more clearly in the next one, but basically we're looking for CA, and so A is going to start at the exact start of the last subinterval. And the width of this is going to be 0.1 multiplied by the width of the A subinterval, so that's 0.2 equals 0.02. All right. Next thing, well, we have 0.6 is still the start of our subinterval, and we want to add on some proportion of the width, so 0.02, and that proportion is going to be, what's the next thing? We have to do B, so I think that's 0.2. Yep, that's right. And that's going to be 0.604. The width of this is just going to be, again, we're going to multiply by the width of this B interval. So we're going to have 0.02 multiplied by 0.4. This is 0.008. We add on 0.604 plus, well, B is going to be, well, the stop is 0.7, I think. Is that right? Yeah, so 0.7 of 0.08. This is going to equal 0.6096. I did that before, so I remember. And the width is going to be 0.008 multiplied by the length of this algorithm, of this width, which is 0.3, which is going to be 0.0024. All right, so our encryption, finally we can do this, is we have the beginning of our subinterval for the encryption is 0.6096, and it will end at the width of the subinterval, which is going to be 0.6096 plus 0.0024, which I am going to just go through, and that would be this. And so our encryption is 0.61. Decoding is also kind of difficult with this encryption algorithm. I like to do it with this following method that is basically, I call it the hamburger method because it kind of looks like a hamburger. What I'm going to do is I'm going to take, at the very beginning, I'm going to just draw out a length of 0 to 1, right? And I'm going to mark off the 0.2, that's where the A's are going to be, 0.6, that's where the B's are going to be, like any code that starts with a B, 0.75, that's where the C's are going to be, 0.70, sorry. And this is going to be the stop, right? So I'm just going to start off by doing that. And I'm going to write down exactly where my code is on this interval. Yeah, so we know immediately that the message starts with an A. What I do next is I'm just going to blow up the subinterval to a length 0, 1. So I'm going to do blur, and this is going to be my new subinterval, right? So if this was the burger bun, this is maybe like the lettuce, the mayo, depending on how awful this encryption, how awful this decoding is going to be, you're going to get many layers to your burger. So this is between 0 and 1. And well, what do we have to do to get a number here over to this subinterval? Well, let's say that that's numbers x. We're going to subtract off the beginning, so that's subtract 0, and divide by 0.2. That subtracting is going to become a lot more obvious when we get to the next step. Right, but for now I'm just going to state that. So we had 0.08 divided by 0.2, that's going to be 0.4. Is that right? Yeah, looks like it. So in this newer subinterval, our message gets put over to 0.4. We have A is still at 0.2, 0.2. This is A. Oh god, this is an awful diagram. B is at 0.6, C is at 0.7, and stop is everything after that. All right, so we know that now the next bit of our message is going to be, well, it's in this area, so it's going to be a B. We do the same thing. We blow this interval up. We take S, X minus 0.2. divide by the length of the sum interval, which was 0.4. Yeah, so this is why subtracting is, this is also why I guess subtracting is was done in the last step, even though we were just subtracting 0, just because it's consistent with this step. And so what we're going to find is we're going to find that 0, 1, our message is going to go from 0.4 minus 0.2, 0.4 is 0.5, so it's right in the middle. It's going to add another b. We can do the exact same step again, so this is going to be, this was 0.2 because it's in the b subinterval, so it's x minus 0.2 on 0.4 is going to go to 0.5 minus 0.2 on 0.4 is equal to 0.3 on 0.4 is equal to 0.75. Hey, that's a stop symbol. And so, with this burger method, we have decoded our message. Once you get used to it, it can go pretty fast. There is also a table method, but it's very much the same thing. Not conducive to teaching though, because you have to actually draw out those same diagrams to explain exactly what's going on anyway. No burger as well. What the hell? All right, so that's arithmetic coding. The last bit is going to be LZ 78, and hey, it's 1:50. This will take about 10 minutes. We're right on time. All right. So, LZ 78 is a dictionary method, which basically means that we encode and decode by building up dictionaries. Very different to what we've done before. All right, so again, here is just a bunch of slides telling you exactly how to do this. I'm going to pause here, so anyone that wants to read these can, but I'm just going to go through an example. So, use LZ78 to encode abacadabra, whatever it is. So, the way that we're going to do this is we're just going to draw out our dictionary. So, the 0th element in the dictionary is always the empty set, because we have to start off our dictionary being empty, and then we just fill it up. And this is the LZ78 method, is just filling up your dictionary. And yeah, let's just go through this. So, the first entry in our dictionary is going to be, hey, we're going to look at this message. We're going to say, hey, do I recognize any elements in our dictionary already, reading left to right? The answer here is no, because A is not in our dictionary yet. And so if we don't see anything, we're just going to append it to the dictionary element that we do have. So there's nothing, so the dictionary element is 0. So we have to, maybe it's better if I just do the example, do the line first, right? So I say 0 because we are appending A to the 0th element of the dictionary to get this first element in the code. All right, so then we just continue. So the second, we are going to have to append a B to the 0th element of our dictionary. And so we add a B to our dictionary. Third, we're going to add a B to a dictionary, and we have B in our dictionary already. So the next element in our dictionary is going to be B appended with an A. So we have BA, which is just going to be the second element in our dictionary, and we appended an A to it. 4 is going to be, well, we have A in our dictionary, but we don't have AC in our dictionary, so we're going to have to take OAC as our new element in the dictionary. That was 1, and we appended a C to it. 5 is just going to be C. Well, we don't have C in our dictionary yet, so we have to go 0C, add C to our dictionary, cross off that. 6 is going to be, well, we have AC in our dictionary already, so we can just say the new element in our dictionary is going to be ACA, which was 4. We appended an A to it. 7 is just going to be, well, we have BA in our dictionary. We appended a C to it, so this is BAC. B's in our dictionary, so we have, is that BA? BA's in our dictionary, so that's 3, and we appended a C. 8 is going to be, well, we have ACA, and we append an A, so this is going to be ACAA. which is going to be 6, and we appended an A to it. All right, and so our output of this encoding is going to be just reading down this output line. So it's going to be 0, 0, comma A, 0, comma B, 2, comma A, 1, comma C, 0, comma C, 4, comma A, 3, comma C, and 6, comma A. Cool. All right, so just to make sure we didn't make any steps.
Wait, I don't remember what happens if you end like how do we haven't seen it before, but you don't extend it off? Like, what if you have that including A?
What do you mean by that? So we have,
like, let's say you take that string and then you put an A at the end.
Uh-huh.
So your last up was 6A.
Uh-huh.
And then you want to process one more A. Right? Like, say like there's an extra A.
Sure. So the question was for people at home is, let's say that we had an extra A at the end of our statement. So how would we encode this? So isn't this, the way I'd write this down is I'd probably write down like, this is going to be 1 and we appended the empty set. Yeah, because that's already in our dictionary. A is in our dictionary. That's how I'd write that down.
Okay, I was wondering if it would be 0 and then A.
It could be 0 then A. Yeah, no, it could be both. In fact, that's probably more correct. This is something that you could search up as well. Yeah. All right, yeah, so that's actually an interesting question. Like if you had an A, what would, if you had like A, yeah, that's an interesting question. Okay, so decoding these are super simple. Oh, I am going to say that there is like a little mistake in these notes that I didn't correct until I found it. I think it's somewhere here. Yeah, I think there's an error there. Is it there? No, there's an error somewhere in one of these LZ78 like just messages here. Somewhere, somehow. All right, decoding. Again, you can read through these slides, or you could just go through an example. So, decoding something in LZ78. What we're going to do is we're just going to build up our dictionary and then read down the dictionary. So, the 0th element in our dictionary is always empty, so 0, empty set. The first element in our dictionary comes from this, so 1 is going to be the 0th element, we appended a B to it. 2 is going to be this element, so it was the 0th element in our dictionary that we already have, we appended an A to it, so it's A. 3, C. 4 was the 2nd element in our dictionary, so this one, we appended a B to it, so it is a B. 5 is going to be this one, so I'm actually going to cross was the first element, we appended a C to it, so this is going to be BC. Then it's going to be 5, we appended a B to it, so this was appended a B to it, so 6 is going to be BCB. 7 is going to be 4, we appended a C to it, so that was AB, we appended a C, so ABC. And then the 8th element in our dictionary is going to be the 6th element, we appended an A to it, so BCBA. And so the output is just going to be reading down this dictionary, right? So the output is going to be, what's my message? Let's find somewhere on the page to write this. Let's go back to this pen, just for nostalgia. M equals B, A, C, A, B, B, C, B, C, B, A, B, C, B, C, B, A. Oh, all right. So that's how you decode with LZ78. Let's make sure that we were right. We can go down. And yeah, that's the end of section 3, which, hey, right on time. Join us tomorrow for when we go through information theory. I'll be taking that, and then Cyril will take over for the rest of the course. All right, wonderful. Thank you everyone for being here.